Okay, everybody. Right, we're into the home stretch. Here we go. So, what you've noticed is that for every one of these environments of deposition, we have different sediments. The size of the sediment is changing, the makeup of the sediment is changing, the types of fossils we get in the sediment is changing, and the sedimentary structures that we get in the sediment are changing. So that means that for every environment of deposition that we have, something is slightly different. It's distinct in some way. So if we look at this diagram here, what can we see? Well, this is the idealized sketch of what we get if we're off the coast of a continent, for instance. So obviously here we have the continent here, beach here, delta there. And you can see, though, as we come off into the marine environment, we get a change in the sedimentary, when the environment of deposition. So as we come off the coast, you can see that we move into an area which is dominated by sand. So this area is essentially like the beach. It's an area that's going to get churned up by wave action all the time. So in this area, we're going to get quite a few fossils. We're going to get lots of ripples. We may even get some dunes forming. Now, as we keep going and we move into slightly deeper water, the sand will eventually start to give way and it will begin to be replaced by mud. Now, this mud is not going to be essentially like the sand. It's going to consist of obviously very, very fine layers, these laminations. And once again, though, we are going to see quite a few fossils in there. Now, the thing is this mud is normally not going to be disturbed by the waves unless there's a very, very strong storm. So this layer, this area here is going to consist mostly of very finely laminated mud, which once again is going to be full of fossils. And then finally, as we keep going, if conditions are correct, we will eventually leave this muddy area and we will go into an area which is dominated by limestone or carbonates. So what you can see is that for each of these different areas, we have a distinct zone, essentially, a distinct environment, which is going to produce distinct rocks with distinct structures, distinct compositions, and of course, distinct fossils. And so we can identify them from one another. And so what we did is we used this fact that we could identify these different environments from each other to essentially produce a term. And that term is facies. And so a facies is defined as a body of sediment recognizably different from adjacent sediment deposited in a different depositional environment. So in this diagram here, we have 6 different facies. We have the continental facies here, probably a fluvial facies, a river facies. We have the delta facies. We have the beach facies. We have the sand facies, which is a marine facies. We have the shale facies, also marine. And we have the limestone facies, marine. So we have essentially 6 completely different environments which are going to produce distinctly different types of rock. Now, once we realized that we had these facies, one of the things that we noticed is that over time, these facies will actually move. So what we began to see in the rock record is, over time, we would see things like the shale facies would steadily, over time, start to move over the top of the sandstone facies. So we had to work out, well, why is that happening? Sorry, I've got a really itchy nose. So, the shale facies would start to come over the top of the sandstone facies. Or in some instances, the sandstone facies would start to move over the top of the shale facies. So the question becomes, what's going on? What's causing this? So it was realized pretty quickly that what was happening was the result of changes in sea level. So if we look at this diagram here, what have we got? So we have this orange layer. So we have the sands, which is dominated here by the speckles. We have the muds, which is the area which is made up of dashes. And we have the carbonates, which is the area made up of this brick pattern. So this is our situation. Sands, muds, limestones. Sands, muds, limestones. Okay, so this is the situation where we have sea level A. Now what's going to happen is sea level A is going to rise and it's going to move to level B. So the sea level goes up. Now this obviously means that the sea will move further onto the land. And as the sea moves further onto the land, well, that means obviously the quartz facies, the sand facies here, is going to start migrating with the sea, isn't it? So the sand facies is going to start migrating onto what was dry land. Now, this means that the mud fascies, the shale fascies, is actually going to start following the sand fascies. So the shale fascies is also going to start moving inland, and it's going to start moving over the top of the sand fascies. We're then going to have the deepest fascies, which is the carbonate fascies, is also going to do the same thing. It's going to start moving inland, and it's going to start going over the top of the mud fascies. If the sea level keeps rising even further, so the sea moves further onto the land, well, the sand fascies is going to keep following it further and further onto what was dry land. The mud fascies is going to keep going, and it's going to keep covering over, the mud fascies, here, it's going to keep going, it's going to keep moving over the top of what the earlier sand fascies. And the carbonate fascies is also going to go over the top of the earlier mud fascies. And so we can see we have this migration of these fascies depending on how high or low the sea level is. And you will also notice that when the sea level has been moving inland, we're actually going to end up with a very distinct sequence. And it's a sequence which is going to go sand, covered by mud, covered by carbonate. So we're going to end up with a sandstone layer, a mudstone layer, and a limestone layer. 1, 2, 3 in that particular order. And so this sequence of rocks is actually going to be a really good indicator that sea levels are rising. So these changes in sea level produce a very distinct sequence in rocks. Now, when the sea is moving onto the land, it's called a transgression. When the sea is coming off the land and going back into the ocean, it's referred to as a regression. Now, as geologists, we can pick out transgressions and regressions by looking for certain sequences of rocks. So if we go back here for 1 second, you can see here's a sequence of rocks that shows us there's a transgression. Sandstone, into mudstone, into limestone. A regression will be picked out by the reverse sequence. We'll have limestone being covered over by mudstone, being covered over by sandstone. So this sequence tells us the water is getting deeper. This sequence tells us the water is getting shallower. Water gets deeper going up, water gets shallower going up. So the water's moving onto the land, transgression. The water is moving off the land, regression. So a transgression is essentially a vertical sequence of fascies representing progressively deeper water environments. So what we'll get is we'll get finer grained fascies overlying coarser grained fascies. So we'll get the sand being covered over by the mud, being covered over by the carbonate. So what essentially causes these transgressions? Well, marine transgressions can be caused by just a relatively limited number of options. So marine transgressions are normally caused by the melting of polar ice sheets. This obviously releases water into the oceans and the sea level rises. There are other instances that can cause this. During the Carboniferous, it looks like spreading ridges in the middle of the ocean. So if you remember, a spreading ridge essentially is also called a divergent plate boundary. If you remember, divergent plate boundaries are about 1 to 1.5 kilometers higher than the abyssal plain either side. During the Cretaceous, in some instances, we think that the spreading ridges would have been somewhere in the region of 3 kilometers higher than the abyssal plain either side. But obviously, because the spreading ridges were higher, that means they displaced water. And because they were displacing that water has to go somewhere. It went onto the land. So during the Cretaceous, global sea levels were extremely high because global temperatures were very high, meaning there were no polar ice caps. But at the same time, the spreading ridges were also very, very high, which pushed extra water onto the land, which meant the global sea levels were even higher than they should have been. You can also have a change in sea level caused by localized subsidence of the land. So not with the previous two examples is where the sea has risen relative to the land, but there is another possibility, which is where the land drops down relative to the sea. And that kind of change can be caused by earthquakes. However, that kind of change is very, very localized. It will only happen over a very short area of the coast. In contrast, melting polar ice caps and increases in undersea volcanism will cause the sea level to rise globally. So this model is going to kind of demonstrate the basic situation. So here's the situation. So here's the sea, okay, and obviously we have sand fasces right here. And so what's going to happen is the sea level is going to increase and it's going to start moving onto the land. So there we go. So the sea has started moving onto the land, and we can see the sand fasces have started following the sea there. So the sand fasces have been migrating inland, and now that means the deep water fasces, the mud fasces which were here, have started to migrate over the top of the sand fasces. Excuse my daughter just coming through field of view there. So the mud fasces have just gone over the top of the sand fasces, and the sea level is going to go even higher, and now we're going to have carbonate fasces coming over the top of the mud fasces. So remember, the carbonate fasces are the deepest water fasces. So this water was shallow initially here, and then as the sea level rose and rose further, the water level got deeper, and so these initially shallow water fasces got replaced by deeper water fasces as the sea level kept going up. Once again, sandstone, mudstone, limestone. There we go. So that's a transgression, and it's going to produce the sandstone, mudstone, limestone sequence. So what about a regression? Well, a regression is when the sea comes off the land and goes back into the ocean basin. So a regression is going to represent a shallowing of the water depth. So what we're going to see is we're going to see coarser grained fasces laying over the top of finer grained fasces. So a regression is going to be caused by things like a build-up of the polar ice caps. That's going to lock water away so it can't go back to the oceans. So essentially the sea level is going to start dropping. It could also be caused by a localized uplift of the coast during an earthquake. So here's our reverse situation. So here we go. This is where we were before. We have sand, sand, shale and carbonate. And now what's going to happen is the sea is going to start coming off the land and back into the ocean basin. So we're going to see the mud fasces here are going to start getting covered over by the sand fasces here. And we're going to see the mud fasces here are going to start coming back over the top of the carbonate fasces here. As the sea level drops, this change is going to become more and more pronounced. So we're going to have the carbonate fasces here getting covered over by the mud fasces, because what was deep water is now becoming moderate depth water again. And we're going to have the sand fasces is going to keep coming out over the top of the mud fasces, because what was moderate depth water here is now becoming shallow water again. And then eventually this is going to continue. So we're going to get carbonate, limestone, covered over by mud, covered over by sand. And so we're going to get the reverse of the transgressive sequence. In this case, we're going to have limestone overlain by mudstone, overlain by sandstone. And this is a regressive sequence because the sea is moving back into the ocean basin. So what causes transgressions and regressions? On a local scale, tectonic uplift, earthquakes. So an earthquake can cause areas of the coastline to be lifted up or to go down. We can also have changes in the coastline due to what's referred to as isostatic adjustments. So that's essentially when the Earth's surface will literally bounce. So imagine the last ice age. So during the last ice age, there were areas of Canada and Russia, Scandinavia, even Scotland in the United Kingdom that were covered by really big, thick ice sheets. You know, a couple of kilometres, 3-4 kilometres of ice, just pushing down that piece of crust. And essentially, what it was like is, you know, me standing on a trampoline. When I stand on a trampoline, well, it causes the trampoline to warp downwards. Exactly the same thing happened with the ice. The ice was pushing down on the crust and it caused it to warp down. Well, at the end of the last ice age, the ice melted, and so the weight was then lifted off that crust. And so what's been happening since the end of the last ice age, that crust has been bouncing up because the weight is now gone. And so obviously, once again, that's going to cause coastlines to steadily rise because the weight is gone and they're bouncing back up again. We can also have sediment compaction. And sediment compaction is purely caused by sediment settling. So if you have a pile of sediment off the coast and it's quite thick, over time that sediment will slowly begin to settle and the layer will become thinner and thinner and thinner. It will compact itself. And so if that happens at the coast and you've got a big sequence of sediment that starts compacting itself, well, that sequence becomes smaller and smaller and smaller. And so that can cause the coastline to literally drop into the ocean. Now, those are local. So earthquakes, isostatic adjustments, and sediment compaction, those are all local options. What about global? Well, as discussed, climate change. So climate change, when the world gets hotter, ice caps melt. When the world gets cooler, ice caps grow. So when the world gets hotter, sea levels rise. When the world gets colder, sea levels drop. And there's also the aforementioned tectonic activity, which, as I said, during the Cretaceous especially, there was more activity at divergent plate boundaries. That meant the divergent plate boundaries were much, much higher than they were now. That meant they displaced seawater, and that seawater had to go somewhere. It went onto the land. Because remember, modern divergent plate boundaries are about 1 to 1.5 kilometers higher than the abyssal plain either side. During the Cretaceous, those divergent plate boundaries would have been somewhere in the region of 2 or 3 kilometers higher than the abyssal plain either side. That meant they would have displaced a lot more water, and that water had to go somewhere, so it went onto the land. So now we've established how rocks and stratigraphic columns help us track changes in the environments of deposition experienced by an area through time, but we can also use them for something else. So we can use these layers of sediment for what we refer to as correlation. So correlation is simply the ability of a geologist to match up layers of rock at different locations. So if I can match up one layer of rock to another layer of rock, then essentially I've linked that layer of rock. And sometimes we can do that over, meters, kilometers, tens of kilometers, hundreds of kilometers, in some cases even thousands of kilometers. You can link up a layer of rock. And that's obviously very, very useful, because if geologists can do that, it gives us some idea of what's happening to that layer of rock. So the question is, well, how do we correlate between different locations? Well, the first thing we need to do is we need to try and match up layers of rock, and we normally do that based on the age. So I know that sounds a bit silly, but if we're trying to link up, if we're trying to correlate between locations, most of the time we don't actually care about what the rock is. So it's not like I'm going to location A and finding a sandstone, and then going to location B and finding a sandstone and saying, well, those two rocks are the same, therefore they must be the same age. No, we don't do that. What we actually do is we spend most of our time saying, okay, what's the age of the rock? So if I go to location A and I find a sandstone that's Permian in age, and I go to location B and I find a limestone that's Permian, well then I correlate those, because although they're different rocks, they were forming at the same time, therefore they correlate. So the first way of correlating is using fossils. Using fossils will help me to find rocks which are the same age, and I can then correlate them together based on their dates, their ages. Now, sometimes we can use certain layers of rock if they are very, very distinct, and these are referred to as marker horizons. So sometimes in a sequence of rock, you are going to have a layer of rock that is genuinely rare. And if you have a genuinely rare layer of rock, then you can try and use that layer of rock as a marker horizon. So if I go to location A and I have a black limestone, that's a limestone that's very, very rich in organic material, so it has a dark colour. If I go to location B and I find a black limestone, same thing, limestone full of organic material, well, that is relatively rare. So chances are that black limestone at location A and the black limestone at location B are the same layer of rock, and therefore I can correlate them. If I want to be more dangerous, I can also try and link similar lithology. Lithology means rock, within the same sedimentary sequences. So now this one is dangerous. So if I'm going right, well, this sandstone is 50% quartz and 50% feldspar. That sandstone is 50% quartz, 50% feldspar. I'm going to correlate them. Dangerous, but if you really push to it, you can do it. Sometimes you can get super lucky And within your sedimentary sequence, you can actually have something like a volcanic layer, maybe a lava flow, or maybe some kind of pyroclastic material. Now you can send that to a lab and you can have the minerals in it dated through radiometric dating, and it will actually give you a numeric age for that layer of rock. Now if you have at location A, you have a pyroclastic layer in your sedimentary sequence, and that pyroclastic layer is 400 million years old. You have a pyroclastic layer at location B, which is 400 million years old. They correlate. Great. Therefore, you have correlated those layers of rock, and you know they match. Now, something else that you can use is a magnetic reversal. Now, I know this was a long time ago. We have touched on this. Magnetic reversals are where the poles flip. So if you remember, every once in a while, the Earth's poles will change. North becomes south, and south becomes north. And these changes in the poles are reflected in the minerals in the rocks. So we can actually see the remnant signature of this change in the minerals in the rocks. So we can actually look at the sequence of rocks and we can look for these magnetic reversals. And if we can measure them, we can use them to link up pieces of rock over quite large distances. The final option to try and link up rock is we can put together rocks based on their position in a sequence. So if I have a sequence of rocks that goes mudstone, sandstone, mudstone, limestone at location A, and I then go to location B and I have mudstone, sandstone, mudstone, limestone, well, I can say, right, that's the same sequence of rocks, therefore they are probably going to correlate. Once again, risky, but you can use it if you want to. So the aim is to try and correlate rocks from widely different locations, and as such allow you to work out what's happening over very, very large distances. So this is what we try and do. So here's location A and here's location B, and in this instance it's a very simplified diagram because we're linking up individual rocks. So what have we got? Well, here we have a grey limestone. We have a grey limestone over here. So I could say, right, this is the same layer of rock. I'm going to correlate them. I also have a sequence. So I have a grey limestone here. I have some kind of mudstone here. And I have what appears to be a beige limestone here. On this side, I have a grey limestone here. I have a mudstone here. And I have a beige limestone here. So once again, we have the same sequence: limestone, mudstone, limestone. Limestone, mudstone, limestone. So we can link those together based on position in the sequence. So, we can link those two different sets of units together. Now, where does this actually become useful is where we can do it over large distances. So here we go. So this is a nice example. So here we have a situation where we have several boreholes have been drilled into the earth, and essentially they've marked out where the different layers of rock are located on that borehole. And what the geologists have done is they've actually linked up the boreholes, linked up the layers of rock they've linked up the layers of rock between the boreholes, so you can actually have a three-dimensional view of what's happening to these layers of rock. And so you can see, for instance, this green layer of rock here essentially disappears going this way and disappears going this way, and by the time it gets to this borehole and this borehole, it's gone. So you can see what's happening underground in both 2 dimensions and 3 dimensions using correlation. And that's extremely helpful, because once again, you want to know what's happening underground as a geologist, because it's important if you're in the oil industry, the mining industry, the environmental industry, a hydrologist. You need to know this information because you need to know where things are located or where certain fluids, for instance, might be moving if they are in the rock. So these two diagrams here kind of give you a very nice example of how we correlate between layers of rock. Well, okay, so let's start with a simple one. This layer of rock here is igneous, 231 million years old. This layer of rock here is igneous, 229 million years old. Pretty much the same age, they correlate. So then we have position in the sequence. So then we have essentially mudstone, so grey mudstone, beige mudstone, grey limestone, breccia, red sandstone. So we have the same sequence here and here, therefore we can say, right, they probably match up. They're probably the same age. Now, in terms of rock type, that's obviously very dangerous, but you can go, right, red sandstone here, therefore they're the same age, let's correlate them. Very risky, but okay. We have fossils here, we have fossils here and the same fossils here, therefore we can use those to correlate. I've done numeric age already, and then we have magnetic age. We can see that this layer here has a magnetic sequence going reversed, normal, reversed, normal, reversed. And this layer of rock here has the same sequence, reversed, normal, reversed, normal, reversed. Therefore we can say, right, these are probably the same age. So it's all this correlation between different areas is very, very important to geologists because it helps us know what's going on, and that's very important to geologists in trying to work out what the geologic sequence of events is for an area. Okay everyone, so that's it. So that's the end of this presentation. Have a good day.